Geography 243, Remote Sensing. Well, we've gotten through the first few parts of our diagram 1.1, and we've gotten to the point where we're beginning to sense the radiation that's found its way back out into outer space using spaceborne sensors on platforms, satellites that are operating in principally in low Earth orbit. So this image here, this artist's rendering, is of the Landsat 7 satellite. Really the latest, with the exception of Landsat 8, which has now been launched and is undergoing testing, the latest satellite in the Landsat series, which dates back to 1972. So again, there's a reminder, this is what we're looking at. And so I need to update this diagram, but you can see Landsat 7 was launched in 1999. Landsat 6 did not achieve orbit. Landsats 4 and 5 fabulously successful. 5 lasted all the way out to about 2011 or so before it was finally began to fail and was decommissioned. Landsat 4 also was decommissioned earlier in this century. Landsats 1 through 3 principally used the multispectral scanner system that was a lower resolution, fewer channels system that really got us started, whetted our appetite for what was to come with the Landsat program. Here's some links to some videos and other resources for you to review and to learn a little bit about Landsat, the Landsat 8 LDCM satellite that is going to be the future of remote sensing, not just here at DePaul, but a lot of places, and it's going to be really the main platform that you guys are going to be using. Many of you guys are going to be using in your careers. So when you look at the Thematic Mapper, and this is Landsat 4 and 5 Thematic Mapper, and the different channels that we have, you have to relate them to this diagram of the visible spectrum. This is why we keep harping back to this, but these are the ranges in the spectrum and the spatial resolution of each of these channels. You can see it is relatively stable, except band 6, which is in the thermal infrared, right? You see it right out here, has a lower resolution, 120 meters, which is quite a large pixel by by our standards in Earth remote sensing. So again, compare that to the Landsat 7, where you have a little bit more precise channel boundaries in terms of wavelength, and we have a higher resolution thermal scanner on Landsat 7. Now Landsat 7 didn't work quite the way that we had hoped it would. We only got a few years of relatively error-free data. Most of the data that we've gotten since the early 2000s has had a degraded quality to it, and you may come across this as you're looking at it. Landsat 7 also has this 15-meter pan channel. This was a new addition on Landsat 7, and actually I think we tried this on a couple of the earlier TMs, the 4 and 5 TM, or maybe just the 5 TM, but it failed relatively soon after. So this is a really nice addition, when we do have ETM data, as the data that we work with in the Fukushima plant is Landsat 7, high quality Landsat 7 data. This is a nice chart that compares the spatial resolution and the spectral resolution in terms of wavelength of all of the scanners in the Landsat program, all the digital scanners in the Landsat program, the MSS, the TM on Landsat 4 and 5, and then the Landsat 7 ETM plus Enhanced Thematic Mapper, and then it compares it to the spot satellites, or a number of the spot satellites from the French program. Again, this is a useful diagram for us. Landsat 7 orbital parameters, you can see them here. The important things are it is sun synchronous, and it returns to the same location very precisely every 16 days. And this is true Landsats 4, 5, and 7, and also Landsat 1, 2, and 3 had very similar characteristics to it, although the reference system that was used was somewhat different, and so you don't have exact overlap on the tracks that you have on 4, 5, and 7. And this is something that we come to accept, but this is one of those fundamentals that makes this system work in the way that it does work. So in the orbital pattern, you can see you have these north to south tracks. This is in the daylight on the daylight mode, or the daylight section of the orbit. And on day 1, this is a 16-day pattern here. On day 1, you have this track, and you don't return back to the adjacent track until 8 days later. And so this is pretty much how it works. And so east to west, you don't really get same-day coverage. North to south, you can typically get same-day coverage, assuming that you have cloud-free conditions, and you're able to get the imagery from on a north to south path, because they're from the same path and they're being imaged at very nearly the same time. Up through the 1980s, this was what we had in terms of data. You could only get data by and large that was collected while the satellite was in range of a ground receiving station. As the satellite passed out of that area, so you can see there's a large area in central Africa and southern South America, and some other parts of Eurasia. As the satellite passed out of that, we had to rely on onboard tape recorders, magnetic tape recorders, that would record the data. And you guys know about the size of the data, about the size that it is. Well, we're recording that on magnetic tape back in the 70s and the 80s. And then it has to be downloaded to a ground receiving station when it's in range of that receiving station. So in some places, the coverage is very spotty before the mid-80s, and actually, it's not so great even within the ranges of telemetry at those times. So after that time, after starting in the early 1980s, mainly with TM4, we began to use these geostationary satellites as data relays, so that we could really get near real-time data from Landsat from practically anywhere on the globe, as long as we were able to transmit data through these geostationary ComSat communication satellites, and then transfer them back down to receiving stations in the United States. So this is just a quick example, and you guys have seen a lot of this, so I can go through this fairly quickly. In this example, we're looking at the Colorado River above the Grand Canyon, and at the junction of the Little Colorado River in the southwest. And so here's a little closer view of the topographic map, and you can see it's a very rough and rugged area. All these brown lines are topographic contours. And so here's channel 1. You can see the range of that channel in terms of wavelength, and here's the histogram for that channel. Here's channel 4, and again in the near infrared, and so you can see it looks somewhat different visibly. Here's the histogram, here's the wavelength range, and here's the histogram for that channel, and the statistics, of course, here. These are Idrisi histograms. And then here's channel 7 in the mid-infrared, and so again looks a little bit different. And so here you can see the histogram for channel 7 and some of the statistics. And then we do have an example of some scatter plots here. And so when you're looking at a scatter plot like this on the x-axis, and this one we're looking at channel 1, and on the y-axis you're looking at channel 4. So highly linear, but the coefficient of determination, the R-squared, is around 78%. So it is highly linear. However, again, that was between a visible and a reflected infrared channel, so it was around 78%. when we look at two infrared channels, you can see much higher R squared, right? So there's much more redundancy between the infrared channels, as there's much more redundancy between the visible channels, typically when we're looking at multispectral data. So again, this is the Landsat system. This is a system that we use, and it will serve us well as a place to start in our understanding of remote sensing.